Well, guys, let's go ahead and dig in. This unit, unlike anything else we've done this year, guys, is going to feel weird. You understand that throughout this year, we've sort of set up this pattern that says one unit builds on the next unit. The units are a combination of concepts and things you've got to be able to do. And we sort of have established this progression throughout the year. Well, guys, what you're going to find is this unit is nothing like that. It has nothing to do with what we've done before, kind of. And it sets the stage for what we're going to do for the rest of the year. And guys, it's also very, very short, and it's very, very mechanical. This is not a conceptual unit. This is very much these are the things that you've got to be able to do kind of unit. So guys, with that said, let me explain to you what we're doing. So up until now, we've been building some foundational ideas about chemistry and principles and properties and how these things behave. Well, guys, for the rest of the year, we're going to be in lab a lot. Like, you're going to see that the remainder of the year, we're in lab mucking around with chemicals, really doing what you thought chemistry was going to be like as you got into this class. We're there a lot. But guys, here's the problem. In order for you to work successfully over there, I need to be able to say, all right, guys, go to the front of the lab and grab the bottle of copper 2 sulfate solution, and you can intelligently go and grab that bottle and use it in a lab. But guys, the problem is you don't know how to lend names to all these chemicals that we're going to be using. So guys, this is what we're going to do today. Some of these words, we're going to start today. Some of these words are going to sound familiar. So today, guys, we're going to start talking about simple salts. And I think you probably remember that salts are the combination of a metal and a non-metal bonding together. We're going to talk about that as we go, and you guys are going to learn to name those things. Then, guys, after our Wednesday break, we're going to learn to write the names and formulas for what are called the polyatomics. They're a little bit more complicated kind of salt. Then, guys, these are actually going to switch. I'll update the calendar today, but we are not going to do a lab on Monday. We're actually going to move it to Thursday. So we are going to learn to write the names for molecules on Monday. Then we'll do a lab on Thursday. And, guys, that's it. You have then learned all the material that you need to learn in this unit, and the test will be the 16th. So guys, don't blink. This goes really fast. It's very accessible stuff, but it's all skills-based. So as you need help, make sure that you're getting the support you need. But guys, this is what this unit looks like. And then McKay, you were asking specifically about the replacement test. So it'll be next Tuesday, 12:45. The deadline's 2 o'clock. Again, like London, if that doesn't work for you, let me know. We can easily work around it. Don't just ask afterwards, ask before. So guys, this is our calendar. This is what we got going. Any thoughts or concerns there? You guys all good? Okay. So guys, today what we're going to do is we're going to learn to write the names for simple salts. So let me get rid of this. Let me grab a hold of this. And guys, this goes fast. I would encourage you to title your notes, Chemical Formulas for Simple Salts. And the date today, I happen to know, February 1st. Just happen to know that. No special reason. Hey, so guys, can I use the word judicious with you? I'm going to do it anyway. So guys, let me encourage you to be judicious about the notes that you take. For example, I'm about to throw a slide up on the wall that I lifted directly out of notes from clear back before Christmas that talks about what metals and nonmetals are and how those things get together to form salts. So guys, if you can read this and agree with it, I'm going to encourage you to not write it down. So when we talk about ions, are you remembering that metals are big and weak? Remember that? They're over here, right? And as we move to the right, the nucleus gets stronger. So metals are big and weak. As a result, they give away electrons and they form positive cations. Does that sit okay with you guys? Okay, then guys, the nonmetals over on the right-hand side are small and strong. As a result, these things take in electrons, and when they do that, they become negative ions. And when the positives and negatives all attract together, these form compounds that we call salts. Does that all sound familiar to you? Are we all okay on that common foundation? So guys, today what we're going to do is we're going to figure out a naming structure for figuring out the formulas for salts. But guys, before we do this, and this is going to be worth writing down because this is new, we need to identify what chemical formulas are. So scratch this in your notes. So guys, fundamentally it goes like this. Today you're going to learn to write chemical formulas for what we call the simple salts. To do that, you need to know what a chemical formula is. So let me just lay this before you. So guys, chemical formulas are simply word and letter groups that we use to represent chemical compounds. And guys, they communicate two types of information. They tell us what and they tell us how many. They tell us the composition of a compound, and then they tell us the ratio of the elements in that compound. So guys, don't write down the examples that I'm about to show you, but I just want to make sure that you're clear on this so that we're all jiving with what a chemical formula is. You guys all okay? So let me share some common chemical compounds with you, and we'll talk about their formulas. So guys, the first one I want to talk about is aluminum nitride. It's Al, don't write it down, but it's Al2N3. And guys, I would propose to you that all of you have seen this before, because this is actually the chemical compound sapphire. This is literally the chemical formula for the jewel sapphire. So what do we now know about sapphire? Well, what is sapphire made of? Aluminum and nitrogen. But it's not one aluminum and one nitrogen. Guys, how many aluminums? 2. Nitrogen's 3. You get the idea? Let me show you another one. Guys, calcium fluoride. Back in the 1940s, this was revolutionary because we learned that fluoride actually, and you guys remember fluoride, right? The most electronegative element on the periodic table. Guys, fluoride actually will bond to the enamel of your teeth, and it locks the enamel of your teeth together, and you don't get cavities. So guess where we find calcium fluoride? In our toothpaste. If you grab your toothpaste tube, it'll say it should say fluoridated toothpaste, and if you flip it over in the back, one of the ingredients could be calcium fluoride. They also use sodium fluoride. But guys, we now know some things about toothpaste. So what's in calcium fluoride? Well, it's calcium and it's fluorine, but it's a 1-to-2 ratio. You get the idea? Okay. But guys, this is where we're headed. Some salts are a little more complicated than this, like this. Guys, this is actually preservative that they put in meat to keep the meat from rotting as it's sitting there on the shelf. So guys, another formula, another salt that we use is actually called barium nitrate. Now guys, we need to slow down, and I want you to write this in your notes. Please scratch this down. Guys, what is barium nitrate made of, and how many of each? And Landon, if you throw one more thing across the room, you're going to pick it all up and leave. Let's do it again. So guys, barium nitrate. What's in it, and how many? So guys, what is barium nitrate made of? And when we talk about this, we're looking for elements. So how many different elements make up barium nitrate? Well, there's 3. There's barium, there's nitrogen, and there's oxygen. Do you see the 3? Now we need to figure out how many of each there are. And guys, in order to figure out how many of each there are, this is kind of like math. Does this too apply to the barium? How do you know? Because barium's not in the parentheses. So guys, if there is no subscript down here, what number is understood to be there? A 1. So guys, there is 1 barium in barium nitrate. Now we need to look at the nitrogen and the oxygen. And guys, when we look at the nitrogen and the oxygen, the two distributes through the parentheses. So how many nitrogens are in this? 2. And what about oxygens? 6. You get the idea? Guys, this is something we're going to talk about more on Thursday, but I wanted to present it to you now. So again, the big idea is that chemical formulas tell us what it's made of and the ratio of the elements. Y'all good? Okay. So guys, this then is where we're going to start getting into the nitty-gritty and talk about how this stuff works. So guys, write this stuff down that you need to. But guys, we're going to start pulling this together. If you don't remember that the octet rule simply says that when atoms bond, they're most stable when they have a shell of 8. You're welcome to write it down. But guys, everything that follows this, I'm going to encourage you to write down because it's new stuff. And if you haven't done so yet, grab your periodic tables because you're about to need them. So guys, here's where we are. We know that when atoms bond together, they want to get 8 valence electrons. That's called the octet rule. But when they gain and lose electrons, in order to get 8, they take on charges. So the idea is we need to talk about something called oxidation numbers. Guys, this is important that you get this written down. So oxidation numbers can also be called oxidation states. When you get to college chemistry classes, some of your professors may call them oxidation numbers, some may call them oxidation states. Either is just fine. You can use them interchangeably in here. But guys, let me define it for you, and then we're going to start playing with the idea. So guys, oxidation numbers are the charges that atoms take on when they ionically bond. So guys, if you'd like a little refresher on this, this is actually something that we talked about before but didn't give it a name. If this is not sounding familiar, you may want to scratch this in your notes. So guys, for example, this. Scratch down a sodium, scratch down a chlorine. Now guys, do this. Add the Lewis dots. How many Lewis dots does sodium have? How many Lewis dots does chlorine have? Scratch them in your notes. If you're not remembering how to figure out the number of Lewis dots they have, guys, remember it's dependent on the group that they're in. So all of these have 1, all of these have 2. The transition metals have 2, 3, 4, 5, 6, 7, and 8. So guys, looking at sodium, sodium has 1 valence electron. It's in the first group. And then guys, chlorine has got 1, 2, 3, 4, 5, 6, 7. So chlorine has got 7 valence electrons. So guys, let's make sure you're clear. What's sodium going to do? Is it going to give away 1 or gain 7 in order to get 8? Give away 1 or gain 7? Well, let's look. Sodium's on the left, right? So if sodium's on the left, is it big or small? Big, weak or strong? Weak. So what does it want to do with electrons? Give them away. So guys, sodium's going to give away an electron. Now look at where chlorine is. Chlorine's on the right, so it's small and it's strong, so it'll take them in. But guys, how many electrons can chlorine take in? Just 1. So this electron is going to go right there, and now they both have 8 valence electrons. Chlorine is full. When sodium loses a valence electron, then the 10 electrons from neon are exposed, and that's full as well. But now guys, do this. When sodium loses an electron, what does its charge become? What's your charge if you lose 1 electron? +1. What's the charge of chlorine if it gains an electron? -1. Do you now understand oxidation states? Guys, that's what oxidation states are the charges these elements take on when they gain and lose electrons. Yeah? That's a great question. And McKay, the answer is it loses its one valence electron, but remember it's got 11 total electrons. So what happens is, can I even do this for you? Let's find a diagram that'll work. Okay, let's do this. So here's the idea. We've got the 1s, and that's full, right? We've got the 2s and the 2p, and that's full. And then for sodium, we've got 1 electron in the 3s. And when that 3s electron comes out, it leaves the 2s and the 2p, and that's full. That's got the 8 electrons, and that's how it fulfills the octet rule, by stripping off that one valence electron and exposing the inner electron shells that are full. Does that sit okay for you? Okay, so now guys, let's do this. Let's tie these numbers to your periodic table. Guys, grab your periodic table and look at sodium. And then guys, look at the abbreviation for sodium, Na. And then look above the abbreviation for sodium, and what little itty bitty number do you see sitting there? +1. Guys, the plus is understood to be there, but guys, that number 1 is this number 1. Do you see the one we're looking at, that little itty bitty 1 right there? Guys, that is the oxidation number. So now go over and look at chlorine. It is an absolute mess. Guys, if you go over and look at chlorine, what charges do you see? So, yep, so +1. Do y'all have +3? Do you have +5? Do you have +7? Do you have -1? Okay, then we have the same periodic tables. Holy smokes. So guys, which one is it? Is it +1, +5, +3, +7, -1? And guys, the answer is, it can be all of those. So what you need to realize is that some of these elements have very, very complex sets of oxidation numbers. And we looked at an example of that. Guys, chlorine's crazy. It can give away 1, it can give away 3, it can give away 5, it can give away 7, or it can take in 1. Go ahead. Yes. That's a great question. So yeah, I love that you're looking. Let's, Kyle, tell everybody what you're looking at. Guys, if you look at the decoder key down in the bottom left-hand corner, do you see where it actually says oxidation states? And then it says bold is most stable. What that means is the number that's in bold is the one that's preferred, the one that happens most frequently. And what do you notice for chlorine? Which one's bold? It's +1, which doesn't make a lot of sense, right? Because we're going, wait a second, we already established that chlorine's on the right, and if chlorine's on the right, it is small and it is strong, and therefore it should want to take in electrons. Well, it turns out, guys, that these elements on the right can also give electrons away. It's through a kind of chemistry that we're not going to get into, but understand, not only can chlorine give away electrons, it prefers to give away electrons. We'll talk a little bit more about this later, but guys, we're kind of stuck, right? Because we're going, wait a minute, we understand these numbers tell us about what these things like to do with electrons, but it's hard to know which numbers to use. We identified that chlorine was -1, but now we're finding out it could be something different. So guys, we need to talk about this, and we need to establish some rules. So continue on with me. So I don't know that you need to write this down, but here's the idea. Many of these elements do have very complex sets of oxidation states. So which ones are we going to use? Guys, write this down. Here's the rules. So which oxidation numbers are we going to use? Well, it goes like this. If it's a metal, we are going, if there's only one, we're going to use it. So guys, sodium can only be +1, so we're going to use +1. But guys, take a look at an element like copper. Element number 29. What can copper be? Do you have +1 and +2? Which one do we use? Well, some of you might be thinking, wait, we're going to use the number that's in bold. And that would be the one that copper tends to do most frequently. But guys, what if that's not the case? What if copper gives away 1? Well, the answer is this. This is how we tell the difference. We use Roman numerals. So guys, if it is a metal, and if it can have more than one charge, we use a Roman numeral to indicate how many it will give away. And guys, if you don't know your Roman numerals, these are they. The I's are 1s, the V's are 5s. If a big number comes before, if a little number comes before a big number, you subtract. If it comes after, you add. Do you remember when you learned that in 2nd grade? That was life-changing for me. So guys, the idea is this. You've got an I, which is 1. You've got 2 1s, which is 2. You've got 3 1s, which is 3. Then V is 5. So this is a 1 and this is a 5, but the little number comes first, so you subtract it. So 5 minus 1 is 4. Then V was 5. Now we've got a big number and then a little number after it, so we add. So VI is 6. And then the last number there, VII, would be 5 plus 2, which is 7. Because that's already got a full octet. That's a noble gas, and we don't need to worry about it. Yeah?
So, you said earlier, like, when you were talking about in the end it doesn't matter, so now you're saying it does?
Oh, if I said in the end it doesn't matter, that's not true. It matters very much. Yeah, if I said that, I misspoke, because no, that's not the case at all. It matters hugely, because if we don't know the charges, we can't build the compounds. So we have to know what they are. So yeah, guys, if you heard me say this doesn't matter, that couldn't be further from the truth. It matters very much. We need to know what the charges are. Is that okay? You guys good on Roman numerals? Okay, so here's what we've established. In order to know the charges, the oxidation numbers, if it's a metal, if there's one, use it. If there's more than one, then we're going to use a Roman numeral to indicate what it is. Then guys, if it's a non-metal, we're going to use the negative charge. You're going, wait a minute, I look at chlorine and most of the charges are positive. Because we are not going to worry about the positive charges for the non-metals. And then, if it can have more than one negative charge, we will use the charge that's predicted by the group. And I'll explain what that means in just a second. And then, guys, we're going to start playing with these. So guys, can you find one where the non-metal has more than one charge? More than one negative charge? Say it again. Okay, what can nitrogen be negative? Oh, sure enough. Good, great example. Let's do this. Take a look at nitrogen. So nitrogen is a non-metal, so we've established that we're going to use the negative charge. But now there's more than one negative charge, so which one are we going to use? And the answer is this. We're going to use the charge that's predicted by the group. So guys, what does that mean? Well, count with me. If you look at nitrogen, nitrogen has got 1, 2, 3, 4, 5 valence electrons. So guys, if it's got 5, how many does it want to get to 8? 3. That's the charge we're going to use is -3. Does that make sense? So guys, if it's got more than one negative charge, we're going to use the charge that's predicted by the group. And so for example, nitrogen will use -3. All right, so guys, let's call timeout and let's do questions. So here's where we're at. We are going to learn to write chemical formulas for salts. We know salts are a positive and a negative ion bonded together. The metal gives away electrons, the non-metal takes them in. We now understand that some of these elements can give or lose many different numbers of electrons. And so what we're saying is this. If it's a metal, if it's got more than one positive charge, Roman numeral. If it's a non-metal, we're going to use the negative charge, and if it's got more than one of those, we're going to use the one that's predicted by the group. So guys, let's take a deep breath, do questions, and then we're going to talk about how to do this, and you're going to get your homework done. Go ahead, Sam.
So if there's more than one, can we use the Roman numeral how many options there are?
No, great question. So if there's more than one, it's not the Roman numeral that tells you how many options, it's the Roman numeral that tells you which one to use. I was hoping for 3-part harmony. So you guys sing the bass line, and we'll let them do the high notes.
Happy birthday. Happy birthday to you. Happy birthday to you. Happy birthday.
Thank you.
Happy
It just flows.
birthday to you.
Thanks, guys.
Happy birthday.
Thank you.
Have an awesome day.
Hey, thanks.
When you get a basket.
I will. Yeah, yeah.
See ya.
Oh, that was so kind. And the world's perfect food, the York peppermint patty. Oh yeah, the secretary down in the front office buys a whole Costco box of these things for me because she knows I love them. It's a beautiful thing. So Sam, did I answer your question? Okay, so the idea is this. Say, for example, we're looking at manganese. Look at manganese on your periodic table. Not magnesium, but manganese, element 25. And you're like, oh, poop. Manganese can be +2, +3, +4, +6, +7. Which one are we going to use? Well, if you want to use +2, Roman numeral 2. If you want to use +3, Roman numeral 3. And so that's a great question. And the answer is you'll be told. Until we get into lab. And then what's going to happen is when you get into lab, we're going to do this backwards, and you're going to be handed a bottle, and the question is going to be, which one is this? But we'll get to that. You guys okay right now? Okay. So guys, this then is what we're going to do. Moving forward, you guys are going to learn to write chemical formulas, and I'm going to give you some rules. Maybe worth writing down. But guys, here's the deal. I'm going to suggest to you that you already know the first 4 rules for writing chemical formulas. So guys, don't write this down, but watch. Ready? Salt. But guys, this is table salt. There are thousands of different salts, but this is table salt. So guys, talk to me about what's in here. What is table salt? Sodium chloride. Don't write this down. But guys, this stuff is sodium and chloride. And can anybody give me the chemical formula? NaCl. Is this earth-shattering to anybody? No, you ready? Then guys, what that tells me is that you actually already know the rules for writing chemical formulas. Write them down with me. Guys, oh boy. I can never switch like that. It screws things up. So guys, rule number 1 is this. And you don't need to worry. Don't write down the stuff in blue. Just write down the stuff that comes up in black. So guys, rule number 1 is this. When you write chemical formulas, it's always cation first. They are always written cation first. But guys, I would propose to you that you already knew this, because this looks stupid. CLNA? Not so much, right? Guys, you know that it's NaCl and not CLNA, because that looks dumb. So rule number 1, it's always cation first. Rule number 2, salts have a neutral charge. The positives and negatives balance out. But guys, I would propose to you that you knew that as well, because you know that table salt is not NaCl2. Why is it not NaCl2? Well, sodium's +1 and chlorine's -1, and you only need one of each for those to cancel out. Rule number 3. When you name salts, the name of the cation does not change. But again, I would propose to you that you already knew that, because guys, you know that table salt is not sodiumide chloride. So guys, the positive ion, sodium, doesn't change. But what about the negative ion? Well, that's rule number 4. When you look at the anion, you drop the ending and add IDE. But you already knew that as well, because you know that table salt is not sodium chlorine, It's sodium chloride. So guys, these are rules that you understood simply based upon table salt, but now we're going to put them into practice in other settings. So it's always cation first. They have a neutral charge. The name of the cation doesn't change. The name of the anion, drop the ending at IDE. So guys, there's one more thing that you need to know as a rule. Then I'm going to show you the steps. Then I'm going to do 3 of these with you, and then you're going to do your homework. You ready to go? Okay. So guys, we already talked about the idea that back in 2nd grade, you learned Roman numerals. So what about this? Guys, what grade was it when you learned about least common multiple? Maybe 3rd or 4th grade. But guys, we need to go back to 3rd or 4th grade and remind ourselves about least common multiple. So rather than define this for you, guys, let me just put it to the test and let's talk about least common multiple. So you ready? Don't write this down. Don't write the example down, but check this out. So guys, what is the least common multiple of 4 and 6? It's not 2. That's the least common factor. What is the least common multiple of these? So we need to know the multiples. So the multiples of 4 go 4, 8, 12, 16, and so on. And then, guys, the multiples of 6 are 6, 12, 18, 24, and so on. Now, where's the least common multiple? That would be 12. So, guys, the question becomes this. Let me show you where we're going. Why do we care about the least common multiple? Well, guys, check this out. Imagine that we have an element, a metal, that has a charge of plus 4. And then imagine that we have a nonmetal that has a charge of minus 6. The question is this. Where is the first place we can get the positives and negatives to balance? At 12. So if we have 1, 2, 3 of the positive atoms, that'll give us a charge of plus 12. Then if we have 1, 2 of the negative atoms, that will give us a charge of negative 12. And that's the first place that these will meet up, is with 3 positives and 2 negatives. So guys, the bottom line is this. We worry about the least common multiple because it's used to determine the charge at which the positive and negative charges will balance, and this determines the ratio of elements in the compound. So guys, we're almost done. If you would like steps for how to write these chemical formulas, I'm going to give them to you. And then, guys, we're going to do 3, and then you're going to get your homework done. Which brings up an important question. Why do we call it homework if you do it at school? There was this big movement in education about 20 years ago where these educational philosophers were pushing that homework should be something that can only be done at home. It was like, scavenge through your cabinets and find a stick. And yeah, it was bad. See? Yeah. Well, actually, it's funny. I didn't even think about this. You may have an extra credit project in a couple days that can only be done at home. I'm going to talk to Miss Call about it, but we'll see. All right, so guys, here we go. Steps for writing chemical formulas. If you want these, feel free to write them down. There are 5. And then, guys, we're going to apply these in 3 different settings. Sam, I think you're going to find that when we look at one of these, it's going to answer your question better about Roman numerals. So, guys, the steps go like this. Number 1, write down the abbreviations. If your handwriting is as bad as mine, I'm a left-handed guy, guys. I'm like the pinnacle for bad handwriting. Take your time and do this well. If you're a girl and you tend to write, not that it's only girls that do this, but if you're all like flowery and hearts and star, guys, big letters, little letters, abbreviations. Number 2, figure out their charges. You may need Roman numerals. Number 3, figure out the least common multiple. Number 4, figure out how many of each ion you need. And then number 5, write the formula using subscripts. So So guys, literally, we're going to do 3 of these. And very quickly, you're going to get so good at these that you could do today's homework assignment in about 4 minutes. No, the top of it anyway. So guys, all we're going to do is we're going to apply these 5 steps 4 different times, 3 different times. And then we'll be good. You guys all caught up? You okay? I don't want to go too fast, but y'all have this at one? We're good? Okay. So guys, it goes like this. We are going to now look at 3 examples of these. Obviously, examples are nice to have, so here we go. So we are going to write the formulas, chemical formulas for these 3 compounds. So guys, the first one we're going to do is calcium nitride. Bless you. So guys, let's set the stage. First of all, find calcium on your periodic table. Calcium is element number 20. And while you're there, what's the little number that's up above calcium? A 2. Now guys, you will not find nitride on the periodic table. But remember the rule, drop the ending and add IDE. So what ending did we drop for nitride? What is it? Nitrogen, sorry, it's nitrogen, right? I asked for the ending, that's not, yeah. So guys, the element is nitrogen, and we change that to nitride in the same way that we change oxygen to oxide. So guys, we're talking about nitrogen. So now let's start putting this together. So step number 1, write down the abbreviations. Guys, calcium is big C, little a. Capitalization matters. Anytime you have a 2-letter abbreviation, the first is capital, the second is lowercase. Then guys, nitrogen is nitride. So now we need charges. And you guys already told me the charge of calcium. What is it? +2. But guys, you'll notice that I didn't ask you for the charge of nitrogen because we know that it's complicated. But we also talked about how to sort out the complications. So nitrogen is second, so we know that it has to be negative. But guys, it could be -2 or -3. Which one are we going to use? The one predicted by the group. And guys, the idea is this. Nitrogen has got 1, 2, 3, 4, 5 valence electrons. That means that it needs 3. So we go -3. Yes, always. That will never change. Always. Okay, so now guys, we need to know the multiples. If you can do this in your head, knock yourself out, but I'm going to write them down. So guys, the multiples of 2 are 2, 4, 6, 8, and so on. The multiples of 3 are -3, -6, -9, -12, and so on. So guys, where's the first place the positives and negatives line up? At 6. So it's here and it's here. So the least common multiple, lowest common multiple is 6. So this is the idea then. We need 1, 2, 3 calciums in order to be +6. So that means we need 3 calciums. Now guys, how many nitrogens do we need to be -6? 1, 2. So this then would be calcium nitride. 3 calciums gives us +6. 2 nitrogens gives us -6. And that would be calcium nitride, Ca3N2. You okay? Now guys, here's the thing. Miss Call and I sat down to talk about this, and we were like, we wonder if students really grasp this idea of clustering of charges creating greater charges. And so we actually put this together. Let me show you how this works conceptually to give you a better sense of this. So guys, same compound, but here's the deal. We have a bunch of calcium and we have a bunch of nitrogens. Watch how this works. If we put 1 calcium in the box, what's the charge inside the box? Well, it's +2. But now, guys, let's throw a nitrogen in there. And if we throw a nitrogen in there, now what's the negative charge inside the box? Well, it's -3. And those don't balance. So we got to keep mucking with this to get these to balance. So let's huck in another calcium. Now what's the positive charge? +4, but that doesn't balance -3. So now let's get another nitrogen. Now the negative charge is -6. Those don't balance. So now we bring in another calcium. Now what's the positive charge? +6. And these do now balance. Well, what did it take to balance them? 3 calciums and 2 nitrogens. Go ahead. That's a great question, and the answer is that compound would not exist. They have to be balanced in order to be neutral, and if they're not neutral, they don't exist. So it would fall apart, and maybe try again. Then it wouldn't be balanced and it wouldn't exist. So guys, where then do these numbers go? Well, we've got 3 calciums and 2 nitrogens, and that leads us to the formula Ca3N2. Do you see how that goes? Okay, so now let's try another one. Guys, the next one that we're going to do is potassium sulfide. So potassium, I believe, is element 11. Is that right? 19. Oh, sodium's 11. Potassium is element number 19. Sulfur is a group made of oxygen. It's directly below oxygen. So guys, the first thing we need is abbreviations. The abbreviation for potassium actually comes from the Latin name for potassium, which I don't know, but it starts with a K. And then guys, sulfide, dropping the ending IDE, is sulfur. So now we need to know their charges. Go look at potassium. What do we got? +1. And guys, does sulfur have a bunch of negative charges? My periodic table here says only -2. Does yours have any others? But what about negative? Just -2? Okay. And realize, guys, that's what London was talking about earlier. The second one has got to be negative. Okay, so now, guys, we need to talk about multiples. Let's try this in our head. Where do +1 and -2 meet up? At 2. So how many 1s makes 2? 2. So this would be K2. Then how many 2s make 2? 1. So this would be K2S. And that would be potassium sulfide. Does that sit okay? Okay, Sam, we're going to do one more. Don't blink. Coming at you. Guys, the last one we're going to do is this. Iron phosphide. Iron is 26, I believe. Oh, look at me. Remember back when we learned that iron is the heaviest element that can be made in stars? I still find that fascinating. So guys, let's get their abbreviations. Iron is abbreviated Fe. Then you will not find phosphide on the periodic table, so what are we looking for? Phosphorus. It's right below nitrogen, and it's a big old P. So now, guys, we need to look at charges. So we look at iron, and what is the charge of iron? What do you get? What am I think I have +3, 2, and 6. What do you have?
2 and 3.
Okay, so for some reason 6 isn't on yours, but that's fine. So guys, which one do we use? The +2 or the +3? We don't know. We're stuck. Because we can't do this. There's no way for us to know which charge to use, and no information is given. So guys, if you were asked to write the chemical formula for iron phosphide, you're stuck. You can't do it. So what information would we like in order to do this? Well, guys, we need a Roman numeral. So let's choose Roman numeral 2. So what that tells us then, guys, is that iron is +2. And Sam, understand, and I know you see this, but that this Roman numeral 2 doesn't mean that it has two choices. It doesn't mean choose the second one. It means that's the charge plus 2. Do you see how that works? Okay. So now, guys, we need phosphorus. Does your table say only -3? That's easy. Okay, so let's see if we can do this without writing out the multiples. Where do 2 and 3 meet up? 6. How many 2's make 6? 3. How many 3's make 6? 2. Guys, we're done. That's it. That's all you got to do. Questions or things you want to talk about? Go, Kyle. That's a great, well, let's look at that. Just for fun, let's do that. Say that this was a 3. So if we do this over, and if we use, if we do that and if we use the 3, then how does that change things? Well, the idea is that this would be Fe and P, and this would be +3, and this would be -3. So where do +3 and -3 meet up? At 3. So we only need one of each. So this would actually be FeP, and that would be iron 3 phosphide. It's a completely different chemical. I have both of these in bottles. Both of these salts exist, but they're radically different. So I chose the 2. We could have just as easily chosen the 3, and both of these exist. That's a great question. And so what's going to happen today is you'll always be told. When we start doing this in lab, I'm going to show you ways to figure it out. Go ahead. No? No? Oh, go ahead. Yeah, so the Roman numeral game, we only play on the first element, the metal. If it's the second one, and if there's more than one charge, then what we do is we use the negative charge, and then we look at the group to figure out which one to use. Somebody else. Alex, were you going to?
How does the +2 not stay on to switch to B3?
That's a great question. And there's it's cool that you picked up on this. Let me show you something. So guys, Alex is picking up on this idea that it's like they're switching. Like the 2 comes down here and the 3 comes down here. There are actually high school chemistry teachers that teach it that way. They teach you to switch. The problem is it doesn't even work here. So it works 95% of the time, but I don't teach it because it doesn't always work. So why did they switch? And the answer is this. So the multiples of 2 are +2, +4, +6. The multiples of 3 are -3, -6, -9, and so on. So where do the pluses and minuses meet up? Well, they meet up at 6. Okay? So how many 2's make 6? 1, 2, 3. And then how many 2's make 6? Or how many 3's make 6? And that would be 2. But sometimes that switching thing won't work. But again, it's cool you saw that. But do you see how it goes now? You guys okay? You guys are awesome. Okay, so guys, as the first day of the unit, let me get the homework packet in your hands. And guys, yeah, you'll get this done. We have like 12 minutes, which is plenty. I think that you do have enough space to just work this on the page. Just work across left to right. And I'll put the answers up on the wall or the screen if that's helpful. Guys, if you did not get to see your test, if you get this homework done, I'm happy to share it with you before you go. If not, you'll need to come on your own time. And if you are not taking the test today after school, please make other arrangements with me before you leave. All right.